one little thing I didn't mention in the last video is that when I follow this first step where you divide the overall numerator and denominator by x to the highest power in either the numerator or denominator, I actually tend to focus on the highest power of x in the denominator. You can do it where you take the highest power in either the numerator or denominator, but for me, in a lot of examples, kind of like the next one we're going to see, it actually works out if you always take the highest power that you see in the denominator. So you can see that I've also added here a little note just to kind of remind myself that whenever you do the limit as x goes to infinity of a constant divided by a power of x, that's going to be 0. This is probably something that would might already make sense to you, because the constant is really nothing in comparison to a massive denominator. But I just wanted to leave that note there also. Okay, so in example 3, we are going to divide each term by the highest power of t that you see in the denominator. And so my work is going to look like this. It's going to be, I'm going to say the limit as t goes to negative infinity of 5 divided by t squared, because t squared is the second exponent. The number 2 is the highest exponent in the denominator. So 5 over t squared minus 2t cubed over t squared. And that's all over. That is all over t squared over t squared plus 1 over t squared. And so you can see that we can simplify this a little bit. And so this is going to be 5 over t squared divided by, or 5 over t squared minus, that would be 2t. Do you see how the t cubed would cancel with the t squared and just leave you a t? So 5 over t squared minus 2t all over 1 plus 1 over t squared. Now let's consider substituting our t to the negative infinity. And this is where this idea might come into play. So if t is going to negative infinity, so it's a negative, really big negative number, and you square that, it's a massive positive number. So 5 divided by that massive positive number is completely negligible, so that would be like 0. And then we have minus 2 times a really big negative number. So we're going to come back to that in just a second. Let's look at the denominator. We've got 1 plus, again, t is going to negative infinity, so if you square negative infinity or square that really big negative number, 1 divided by that is negligible. So essentially, our answer here is going to be just negative 2 times whatever t is going to divided by 1. So really just negative 2 times whatever t is going to. And remember, you technically cannot substitute in a negative infinity, but if you think of it as a very big negative number, then a negative 2 times a really big negative number ends up leading us to what would be positive infinity. So this is kind of an unusual case where we get an answer that is not a number. We get an answer that's infinite, but that's how you would solve this using the strategy from the first side. Okay, example 4. In this one, I want to identify the highest power of s in the denominator. And again, I'm doing this because I'm noting that these are limits at infinity. But in this case, the highest power of s in the denominator is actually not s to the 7th, because you're inside a cube root. But I'm just going to be consistent here. I'm going to do all of this inside the square root. So instead of dividing, instead of figuring out exactly what, the highest power of s is in that denominator, I'm just going to say, let's stick with this and write the following. So s is going to infinity, and I've got the square root of 3s to the 7th divided by s to the 7th minus 4s to the 5th divided by s to the 7th, and that's over 2s to the 7th divided by s to the 7th plus 1 divided by s to the 7th. And remember, this is all inside the square root, absolutely all of this. And so this would simplify. The s to the 7th would cancel, s to the 5th would cancel with an s to the 5th down here, and we would get, when we simplify this, we would get, let's see, that would be the This is the cube root. So we have the cube root of 1 minus 4 over s squared, and that's over 2 plus 1 over s to the 7th. And so, again, this concept is going to come into play again because as s goes to infinity, a constant divided by that squared is going to be negligible, go to 0. Same thing with 1 divided by s to the 7th. And so our answer isn't 1/2. All of this took place inside the cube root, so our answer to this is actually just the cube root of 1/2. It's a little trick when you have a rational function inside some type of a root like we have here. Okay, so similar process for example 5. So I'm going to divide everything by y squared, but notice that y squared is inside the square root, and this is kind of a special case problem. And I really want to point something out in particular in just a second. So when we begin this question, we are going to we're going to take limit y is going to negative infinity, and we're going to say 2 divided by, but we can't say y squared because you see how in this case the 2 minus y is not inside that square root also. So what is the highest power of y in that denominator? Well, you're doing the square root of y squared. So the square root of y squared is actually, it's not y, and I know this is the confusing part of this question, and that's why I'm starring this and saying special case, because the square root of y squared is actually the absolute value of y. Because y squared is going to be positive, and so when you square root that, you're guaranteed to get a positive out, yet y itself could be negative. So we have to put the absolute value there. So when I divide 2 by the root of y squared, then I get 2 divided by the absolute value of y minus y divided by the absolute value of y. And then in the denominator, we can simply take the 7 over the y squared, because that's all inside the square root, plus 6y squared over y squared. Okay, so let me scroll up a little bit here. And so this is going to simplify as, well, let's think about it a little bit. As y is going to negative infinity, this becomes positive infinity because you're doing the absolute value of it. So 2 divided by something that's really large becomes negligible. We'll come back to this in a second. 7 over y squared also going to become negligible. And then the y squareds cancel there, so you end up with a square root of 6 in the denominator, but now we have to address what's happening here. So this is where I use a little bit of reasoning, and I say if y is going to negative infinity, then you're doing the opposite of a really big negative number divided by the absolute value of that really big negative number, right? And so this actually becomes a positive big number divided by a positive big number. So you can reason that this ends up being 1 divided by the square root of 6. Now, again, technically we cannot do math on infinity divided by infinity, but think of substituting a really big number if you don't want to use the symbols like I am right here. But our answer to this one would be 1 over root 6. These last few examples are a little bit quick answer questions. Example 6, for instance, is one where you can do a direct substitution right away. And I want you to see that in a lot of these questions, you should sometimes consider that. And so you don't see the strange setup like what we saw in example 4 or 5. So there's really nothing funny with number 6. And you can just substitute in x going to infinity, and so 4 over x becomes negligible, and your answer is just 5. Or similar type of thing in this problem right here. I think we might be able to do just a substitution. Oh, maybe not. I don't know. Or maybe we can. It looks like if we did that substitution approach, we could reason through things. But there's a couple ways to do this one. You could say, 1 minus e to a really big number all over 1 plus e to that really big number. And so the magnitude of e to that really big number is the same in the numerator and the denominator. And to be honest, these ones are pretty negligible. And so you could probably reason in this question that your answer is just going to be -1. But you could actually apply the other strategy that we've been looking at, where you divide each term by the highest power of that you would have in the denominator. And in this case, you could divide everything by e to the x. So you could say 1 over e to the x minus e to the x over e to the x all over 1 over e to the x plus e to the x over e to the x. And what this is going to do is it's going to show you that as x goes to infinity, that's negligible, and then this just simplifies into -1 over 1. So your answer is just -1. Okay, two more real quick ones. This is another one that I think that we could probably just consider some sort of a direct substitution. I don't really see any algebra that we can do on this anyhow. So if I substituted in a really big number for x, do you see that cosine of 1 divided by a really big number is essentially like doing the cosine of 0? And so the cosine of an angle is the x-coordinate. So if we're thinking about that unit circle, if we're at an angle of 0, what's our x-coordinate out here? That point's 1, 0. So our x-coordinate is 1. Your answer to this question is 1. So with so many of these, we're doing these algebraically, or we're thinking about them just intuitively. You can also put these into your graphing calculator. You could look at these functions. You could look at the graphs of the functions, but you could also look at tables of the functions and say, hey, what happens to the function as I plug in x values that get bigger and bigger and bigger. And so we've talked previously about how you can customize tables, so you can do that, but a lot of times these algebraic techniques that we're learning here work really well. Okay, so this very last one is just a special case problem. And I put this on here because a lot of students would look at this and do some sort of a direct substitution. And if you did, you might see that you have like 1 plus what's essentially 0 raised to the infinity. And that right there is another one of those indeterminate forms. We're going to look at indeterminate forms a little bit later in this chapter, actually, when we talk about something called L'Hopital's rule. 0 over 0 is an indeterminate form, 1 to the infinity. Even 0 to the 0 is an indeterminate form, or infinity minus infinity. It's like when it's an indeterminate form when you say, okay, like something with 0 raised to the 0, you say, is your answer going to be 0 because the base is 0, or is your answer going to be 1 because the exponent is 0? Or, 1 to the infinity, you say, is your answer going to be infinitely large, or is your answer going to be 1, or something like that? Now the crazy thing is, I'm not sure if you recognize this right here, but this is not exactly 1 raised to the infinity. It's 1 plus an iota raised to the infinity, and this is actually the definition of e. And so if we just go into our calculator and we take a look at what e to the first is, that is exactly what you would get if you said, let's see if we could do it here. If I said 1 plus 1 divided by, let's just take a really big number. Let's say like 100 million or something like that. And then raise it to the 100 million power. Let's see if this works. Press enter, and there you go. Yep, you can see we're pretty close. So just kind of a cool limit right there. I thought we would end with that one. So this should hopefully give you enough to take a look at homework 4.5. This was section 4.5. So do that in WebAssign now. And I'm going to put all of the stuff together that we've looked at so far in the chapter, and I'll show you a couple more videos that relate to 4.6, which is really just putting it all together. So good luck. Let me know if you have any questions.